the factors of this are such that this is the smallest. Well, the smallest, now these are positive integers, right? So the smallest L that you can have is just when Q is 1. So it's just 1R. Does that make sense? Right? Because yeah, so just L is equal. Oh, sorry. Am I missing something? I have to show that it's the smallest. Now L will be of that form, right? Because P to the L is E. Right? P to the L is the unit, and L. No, we've let the order of P be R. So in general, L will be of this form. Okay. But L's the smallest one that we can get here, for which these are all factors. So yeah, I think so. So Q is 1. That's the smallest one you can have for positive integers, right? And therefore, so P to the R is E. Therefore, L equals R. And so, what is R? R is the order of this permutation, and L is the LCM. So we've proved it. Okay. So I'll say that in words again because that's what you're asked in the question. You have to. Well, what do you say? So prove that the order of any permutation. So that's R, little r. Okay. That's the order of any permutation P. Is equal to the least common multiple of the lengths, in other words the orders, of its component disjoint cycles. So the least common multiple of these. Let that be L. Okay? So the order of the permutation, that's that, is equal to the least common multiple, which we said was L, of the orders of the disjoint cycles, but that's the same thing as the length of the disjoint cycles, and there it is. We've done that. All right, now the third question. It's sort of basically the question of prove that for the alternating group, so this is question 15, it's the last question in the exercises of the chapter. It's basically, the motivation for the question, I think, is show that the number of even permutations for a symmetric group is equal to the number of odd permutations. I think that's the essence of the question, but they phrase it slightly differently. Now that may seem reasonable. I mean, you know that for every element, every permutation of a symmetric group, it's either even or odd, right? And I've said, just in passing, a couple of times in the theory session, that that in fact the number of odd mutations is equal to the number of even mutations. So now let's actually prove it. So now the question gives you a function. Yeah, so you're mapping between two sets, and you're asked prove that F, the mapping, is a bijection. Okay. Now what's the point? So before I tell you what the function is, I'll sort of have a little bit more discussion. Hence show that the number of elements in A of n, that's the alternating group, remember the famous one, is in fact half of n factorial. Now, so what? Remember, usually it's just represented S of n and A of n. So S of n is the symmetric group of n objects. Okay, all possible permutations of n objects, and the size of that that group is n factorial. Okay, and remember this. This is the set. Well, actually, we proved it a little while back. That it's actually a group. So the alternating group is the group of all even permutations of your symmetric group. And I've stated, I haven't proved, but I've actually said that in fact the size, in other words the order of this group, is half of this one. Okay, so that means that the other half of elements of this are the odd permutations. These are the even permutations. Now, while we're at it, it's not a question, but it's sort of interesting. Think about it. Now, this group of the even permutations, it's a group. Okay. Now, I've not seen it labelled, but let's call the other. Let's call it B of n, and this is the set of all the odd permutations, right? This is the set, by definition, of all the alternating group, as it's called. It's the set of all the even permutations. So let this B of n be the set of all odd permutations. And the point of this last question is to show the size of these two is the same. Now, here's the question I posed to you. I don't know if you've thought about it before, but now this is a subset of that, obviously, right? It's half, as we'll show. It's actually half of this set. Now, symmetric group is still a set, right? Group's a set. So this is half of the elements of this. This is the other half, and these two sets here. Now, there's a group, but also a set. These two sets are disjoint. They're distinct. They have no elements in common, right? This set or group has all the even permutations, and this one has all the odd permutations. Question, if it's not occurred to you before, this set here of all the odd permutations, that set, is it a group? Okay, so can you sort of instinctively give me a quick answer without having to think too much? Which way? See, this, we proved before, this is a group, right? That's a group. And that is a subgroup of this one. This is a subset of that one. But is this one a subgroup? Right? Here, look, let me sort of do it in sort of a Venn diagram. Here's your symmetric group, right? And let's say that is A of n. So that means this is B of n. Okay? This subset here, A of n, is a group. So B of n, the set of all odd permutations, is it a group? Well, I'll start giving you some hints. Now we know A of n is a group, the set of even permutations. Now a group and a subgroup, any group, contains a unit element, right? So let that dot be the unit element of, well, it's the unit of two groups, right? It's this unit here is the unit of S of n, right? It's the permutation that does nothing, just everything gets mapped to itself, right? That's the unit permutation. And this is also the unit of A of n, because A of n is also a group, right? Now, here's the critical point. Remember that any group has one, and only one unit. Right? That was a proof we did way back. Okay, so so this unit here, the unit of the symmetric group, is here, and it lies inside the alternating group, and there's only one of them, right? There's only one unit in this whole S of n. So that means, now since A and B are disjoint, they're completely distinct. A has all the positive permutations, B has all the A has all the even permutations, and B has all the odd permutations. They're quite distinct groups, sets, right? They don't overlap at all, they're completely distinct. And that means that the unit, there can't be a unit in here, because there's only one and it belongs to A of n, the alternating group. Therefore, Bn here, the set here, has no unit, right? Because there can only be one, and that one belongs to the alternating group, it belongs to A. Therefore, there is no unit in B, because you cannot have a second unit, right? Therefore, B of n cannot be a group. There's your answer. All right, that's a bit of a sideline, although sort of interesting. All right, prove that F is a bijection. Now we need to say what F is. So the heart of the question is try to show that the size of this, the order of this group, because we know it's a group, is the same size as the set here. So that group is a set, so the size of this set and the size of this set are the same. In other words, an equal number of even permutations as odd permutations. So here's you're mapping, you're given this, right? It's part of the question. You're mapping the alternating group into S of n minus A of n. And you may say, well, what's the point of that? Well, think about, what is it? Instead of thinking about groups, let's just think about sets, okay? So, group is a set. So